Right, I've recently done this 500mm circular LED display for a LED manufacturer. It's got white and blue LEDs on there. We thought it'd be quite fun, instead of just playing back fixed content, to stick a camera in it. So right in the middle of here we've got one of these little mobile phone camera modules. So I just wanted to talk about actually interfacing one of these to a microcontroller without needing to go to an FPGA to sort of produce a nice simple way of getting a fairly low res output. This is basically 64 by 64. To get a fairly low-res output to effect basically a serial stream to feed into low-res displays. So as well as the camera input, this will actually display off an SD card. Obviously the nice thing about these cameras is that they're small enough you can actually get this in the centre. This is made out of 4 PCBs, so there's a little gap in the centre. But I didn't have a great deal of time to get this running, so I basically wanted a fairly simple solution to just get that camera input to a low-res serial stream. This is actually running at 2 megabits, which is just about enough to maintain 25 frames a second. At that baud rate. I wanted to keep the baud rate reasonably low because we might want a little bit of cable on it. A few years ago I did something vaguely similar with these panels. These are sort of very low-res panels, and for that I used this. This is a fairly low-res CIF resolution, fairly old monochrome sensor, which you can't get anymore. And this was using an ARM7 processor with some very sort of carefully crafted FIQ, fast interrupt code. We also had to slow the frame rate on this was a little bit on the low side, so I wanted to take a fresh look at doing this with a more modern camera module. Now you may have seen I've played around with these cameras before. This was driving it into one of these iPod Nano displays, but because of the high data rate this needed an FPGA. Now for this project, basically the requirements were different. One was that I only wanted monochrome, and the other one was that I only wanted about 64 by 64 pixels. So I wanted a bit more flexibility of doing it on a microcontroller. So I thought I'd have a look at see what was possible, just purely on a software only basis. Now the interface on pretty much all these camera modules is the same. These are the sort of parallel interface ones. Some of the more modern ones use a MIPI interface, but most of the older ones have got pretty much identical interface. This particular one is an OV9650. It goes up to SXVGA 1280 by 1024, albeit at a fairly low frame rate. There's quite a number of these available really cheaply as little modules. One nice thing about the 9650 is the one for which most of the documentation has escaped. It's quite hard to get detailed info on a lot of these. You can quite often find a data sheet, but that doesn't give you important things like all the register setups. But there's about 3 different documents available for the 9650, and it's also really cheap. I bought this. I bought literally a tray of 70 of these cameras for $70, so they're dirt cheap really. Another fairly common one is the OV7670, which I think goes up to VGA again. It is very similar. The main difference is the I2C registers tend to be different, so you need a different set of registers to initialize them, but basically the interface is pretty much the same. You've got basically 3 timing signals. You've got vertical sync, which is goes low once per frame. You've got a horizontal sync, strictly speaking it's horizontal reference, which tells you where the active pixels are. They tend to call it href rather than hsync, but it's pretty much the same thing. You've then got a pixel clock, which is a high frequency clock that then clocks the data out. This is one of the data lines. So if we look at a whole frame, if I wave my hand in front of the camera, you can probably just about see there's some changes going on there. So in addition to this, you need to supply it with a clock, which is typically sort of 12 or 24 megahertz. Some of them have a PLL on board, so you can feed it like 12 megahertz and generate a 48 megahertz internally. Now, and there's 2 problems interfacing these things to a microcontroller. Firstly is the data rate. These things are spitting out data even at QVGA. It's spitting out it's spitting out 7.6 megabytes per second, but also the amount of data. Most micros don't have enough memory to hold a full frame. Now, for what I wanted to do, the memory issue isn't a major problem, but the data rate is. It is possible to just slow the pixel clock on these down to a rate at which you can actually read it as it's coming out. The problem is that also reduces the frame rate. I haven't come across any camera module where you can set it to a low resolution at a high frame rate without having to sort of accept all the data at the speed it's coming out. Now, one advantage I've got is that I'm only interested in monochrome. Typically what you get with each pixel clock, you generally get 2 clocks per pixel. It's usually an 8-bit data bus, and there's 2 common formats. One is YUV, which is intensity plus component. That's typically used for when it's being JPEG encoded. So what you generally get is YU, YV, YU, YV. Now for black and white applications, we can just use that Y, which is the luminous, and ignore the UV. So one advantage of that is that you can only look at alternate pixels, which immediately halves your data rate. The other common format is an RGB 565 format. Now the problem with that is that you need to take each pixel pair, because you got this overlap between the red, green and blue bits over those 2 clocks. And although you could, let's say, take every 4th one, the problem is that you'd have, say, the red bits from 1 pixel and the blue bits from 1 further across, which, although would look generally okay, you'd get nasty fringely twinkly bits at the corners where the bits were different between the 2 pixels. Now I'm implementing this on a PIC32 series device. I've used it quite a lot recently. I quite they've got quite a nice set of features. I've used them on quite a number of projects. But one of the features in particular which is useful for this is DMA, which is direct memory access. If you're not familiar with it, basically what DMA does is on some triggered event, which is typically the same as an pretty much in the case of the PIC32, anything that can create an interrupt can also trigger a DMA. And what the DMA does is it will initiate the transfer of 1 or more bytes of memory, either from memory to a peripheral or from a peripheral to memory. You can also usually do memory to memory as well for doing sort of block transfers. So in the case of, let's say for example, reading data from a serial port, instead of having a serial interrupt that handles that data, it can actually effectively be handled in hardware, which basically means you've got a much lower latency, higher throughput, but also it's not disturbing your main, it's not using up any significant amount of processor time. It does use some memory bus time, but it's generally a lot faster. So basically the method we're using to actually get the data in is we're using DMA. Now there's 2 ways of doing this. One is we can just use an 8-bit parallel input port, so we set the DMA up to read that port and then write it to memory. But the PIC32 has also got this parallel master port, which basically emulates a microprocessor style bus, which gives you external chip select read and write signals. Now one advantage of using that is that you actually get an external read signal, which you can actually use to look at the timing, so you can know exactly when it's reading the signal from the bus, which can be handy especially when you're really pushing the speeds. This is one bit of the camera's data output. Now, although this appears as like it's jittering, it's actually the other end, because we're triggering on the read pulse. What's actually happening is that the read pulse is sometimes getting delayed by sort of part of a pixel clock, and that's because of the memory process in the PIC, in that although the DMA process is much faster than an interrupt, you still sometimes get a very small amount of latency. If the memory's busy when the DMA comes in, it can delay it by a cycle or 2, and particularly if you're on a long line, you sometimes see it jittering by about 2 or 3 processor clocks. But one handy thing about having this is you can actually see how much margin you've got, so you can see it's actually doing the read on this vertical edge here, so you can see we've got a nice clean data sample. If I just send a command to the camera to invert the clock phase, we'll see that it's going to start. It's now starting to occasionally sample at the edge, and you can see on the picture that we're getting garbage data on the occasions that it's sampling in that wrong place. So yeah, that's one nice advantage of using that parallel master port. You've actually got this marker that tells you exactly when it's reading. So if nothing else, it really helps with debugging, making sure that all your counterfacing is right to get actually sample the data when you think you're sampling it. Now, one important thing that you can usually configure on these camera modules. This pixel clock, although this occurs even outside when you're getting data, you can configure it to not occur during the H-sync period. And by default, normally it just occurs all the time, but you can actually configure it via I2C to not be clocking during this H-sync period, and that's actually really important. The reason that's important is that you need to get a consistent phasing between when you're actually reading the data in and the pixel clock. So if that pixel clock is running when you're trying to set up timers and stuff, then it's going to get out of phase. So basically what we do is we take the pixel clock and then we feed that into a timer, and that timer also reloads. So for example, if we want to get every pixel, we set this reload value to 2, so what happens, it will count up sort of 0, 1, then when it hits 2 it will reload the timer and generate the DMA trigger. So by just setting this reload value, we can tell it how many pixel clocks per DMA operation. So for example, for every 1 pixel, which is 2 pixel clocks, we load that with a value of 2, so it goes sort of 0, 1, 0, 1, 0, 1. But for example, we could also sample, let's say, every 3rd pixel, every 4th pixel, purely by setting that. And on our vertical sync interrupt, we just reset everything for start of a new frame. Then on the horizontal sync, we set up for each line that we're going to transfer. So for example, we initialize this timer to 0 so that we know that our clock phasing is going to be right. The reload value will just initialize at the start of the frame because that's never going to change. The other thing we do on H-sync is any line skipping. So obviously, if we're doing any vertical scaling, we just ignore lines. So we just set up a little counter. So we only enable and start this DMA process on the lines we're interested in. The other thing we do is obviously we need to know whereabouts on the line we want to start. So again, we use this timer. So although this is set up to sort of reload, what we effectively do is we set a negative value into this timer. So let's say, for example, we want it to start at 100 clocks. During the H-sync, we load the timer with minus 100. So it will count up sort of through, and then when it hits 0, it will then start the DMA and then reload. So it goes sort of from minus 100 up to 0, and then 0, 1, 0, 0, 1, etc. along the line. And one thing that's important is that this H-sync interrupt occurs here at the beginning of the sync pulse, because obviously the interrupt will take a little time to actually happen and for us to do what we need to do. So all that happens here while the pixel clock is not running. So that's all set up, our interrupt's finished, so we're just ready to, as soon as that pixel clock starts, that's going to start that timer, get us to the point where we want to start sampling, and then do our pixel clock sampling. And the DMA controller has a value that tells it how many bytes to transfer, so that's what stops the process at the end of the line of how many. So let's say we want 64 pixels a line, we tell the DMA controller to transfer 64 bytes. We can also get it to generate an interrupt after it's done that if we need to, which can be useful, but it's not actually essential for what we're doing. The other thing is we're generating the clock for the camera module. We could do this for another timer with an output compare, but on the PIC32 it's got this ref clock out, which basically is a simple divide. It takes a CPU clock and divides it by an integer. The advantage of using that over a timer is that this will actually do a divide by 1, so we can actually feed the full CPU clock 48 megahertz out to the clock input. Now, I don't think these modules will actually take 48 megahertz, but if you're, say, running everything at a slower clock, that could be an advantage. So that just gives you a little bit more flexibility in your clock division ratios. It's also important to actually clock the camera module from the processor rather than giving its own independent clock, again, to make sure that everything stays exactly locked together in the right phasing, because you're trying to hit quite a narrow window when you're sampling these pixels. Even if you're only sampling it relatively slowly, you've still got to actually sample within the window of a single pixel clock time. So if you've got independent clocks, yeah, they're not going to stay in phase accurately enough for that to happen. So it's very important that you actually clock the either clock the camera from the PIC's internal clock or use a common clock to drive both of them. But so the PIC32 is flexible enough that you can generate sort of a reasonable range of clocks using its internal PLL, then divide it as required. And so that a lot of the camera modules have got a PLL as well, so if you need a high, let's say 48 megahertz clock here, you can do that. One issue you quite often run into is that the inputs to these timers tend to have a latch to synchronize them. So if your pixel clock is the same as your CPU clock, you may find you can't actually get it to clock fast enough, because it needs to you actually have to need at least one CPU clock to clock each transition. So yeah, if you're really trying to push the boundaries of speed, things can get quite messy there, and you may get it to work, but it's going to be a bit of trial and error. So we can see here, this is the point where we're actually sampling the image. So this is one complete frame at the moment, and you can see the image on the right, so it's sort of fairly zoomed in. So instead of sampling every pixel, I can sort of sample every 2, every 3, etc. So you can see the sampling spreading out and also the image zooming out. And obviously by adjusting the delays, we can just sample different parts of the frame. So I can just adjust the vertical position. And on the horizontal, this is now showing a single line. Again, we can set the sample position. Again, you see you scroll from side to side. And the zoom factor, again, we're just sampling sort of every 2 pixels, every pixel, every 2 pixels, etc., to get different horizontal zoom factors. Now, one issue you can get, particularly when you're zoomed quite a long way out, because you're sort of sampling small pixels over quite a large area, you get this sort of aliasing effect. So you see that small objects sort of effectively fill a whole pixel, You can see a bit of aliasing on the sort of the window blinds over there, and it sort of looks a little bit sort of sparkly and crunchy. One way around that, if you're only ever going to be using one zoom level, you can actually effectively apply some analog filtering to this by just defocusing the lens. Most of these modules, they tend to glue the lenses, but usually you can actually sort of, with a bit of care, release it, sort of a pair of pliers or something, just to, once the glue breaks, you can then usually screw them in and out. So if I just take this lens out a little bit, about a turn or so, it defocuses it, but now you see we're actually not getting any of that sparkly thing going on. We've got, obviously, with the low res it doesn't matter too much if we're out of focus because we don't have the detail in the final image, but now you see we don't get that aliasing effect because we've effectively added an optical low pass filter to it, so we've got a relatively sort of clean image without those sort of sparkly aliasing type artifacts. Right, so this is how the module ended up. This is just my prototype one that's got lots of wires, just so I can plug onto it to probe it. Instead, I'm just displaying this on a PC. This is being fed into an FTDI high-speed cable, because the standard FT232 will only run at 3 megabaud, but the high-speed one will go up to 6. It'll do other rates like 4 megabaud and so on. So this is just the high-speed. This is the C232 HD cable, and that's just being powered and directly from that. It's just encoded here. There's some code in here that just, you set it a command that says give me an image and give it the parameters, and it just spits the data back at you. So that's basically the final version of it. One thing which isn't very clear if you read the data sheets, you have to read it into quite a lot of detail to find it. If you look at the spec, it basically says you basically got 3 power supply pins on here. You've got 1.8 volt core logic, 2.8 volts analog, and a I/O supply, which is, I think, typically 1.8 to 3.3 to match whatever you're driving with. Now, certainly the OV961555, I don't know about the others, you need to look very carefully in the data sheet, actually have an internal core voltage regulator, and if your I/O supply is above, I think typically about 2.5, you can actually use that, so you don't actually need an external 1.8 volt regulator, but you do need to enable that with an I2C command. Because I wanted to do like a self-contained camera module, I could run everything at whatever voltage was most convenient. So all I've got on this board is a single 2.8 volt regulator, so the PIC is powered by 2.8, the camera, analog and logic supply are running on 2.8, and it's using the internal regulator for 1.8. So literally all we have on this board is the PIC, the 2.8 volt regulator, and some passives, and that's it. There's nothing else on here. Now the actual PIC I'm using is the 32MX170F256B. This is a relatively new device. There's, the 32MX1 series has been around for quite a while, but they fairly recently produced the 170 version, and the main difference in this is got 64K of RAM. Now that's unusually large, particularly on, say, a 28-pin device, to actually have that much RAM, and of course, yeah, that's obviously a very useful thing to have if you're putting images in. You want to be able to capture as much image as you can if you're producing like a general purpose module. Obviously, if you know you're only going to ever want 32 by 32, you can use a lower end version of the chip that's a bit cheaper. But so the nice thing about this chip, it's available in DIP, SO, SSOP, and QFN. It's quite cheap, it's like a couple of quid or so, but it's got that 64K of RAM and all DMA and stuff. So that's sort of basically a complete, quite flexible serial camera module, but monochrome only. In terms of performance, it's actually not bad. I've not really spent too much time playing with sort of squeezing the absolute maximum performance out of this thing, but because we're doing that, only sampling alternate pixel clocks to just get the luminance, we can actually get the camera is basically running in QVGA mode. Most of these cameras do have a few different modes, so you can program them via I2C. So for example, if you put it in QVGA mode, it halves the pixel clock frequency, and you could probably also use that technique to slow down the clock, because some of them support resolutions below QVGA, but say the fact that you might actually be able to get colour out from that by sampling every single clock at a sort of moderate frame rate. Again, I've not really done too much testing, but this will just about get all 320 pixels of QVGA. The main limit, of course, is how much memory we've got in that PIC, and for some just a bit more symmetrical, that's 160 by 120, so that's effectively a quarter of QVGA. So that works quite nicely. And so there probably is some scope. I have actually had this running at 50 frames a second, but the first problem that you hit in terms of speed is if you try to pull that DMA, trigger that DMA too quickly, what happens is instead of triggering when you want it to, it's almost continuously DMAing as fast as it can, and that'll end up being slower than where you want it. So what happens is you'll start get it sampling, not actually sampling all the pixels. You'll get pixels missed out. As you change the zoom ratio, you get to a point where it doesn't actually get any better, because instead of DMAing when the timer says, it's just DMAing as fast as it can, and the data ends up not being properly synchronized to the timer. But there's quite a lot of scope for experimentation. There's quite a lot of scope for tweaking the camera registers to put it into different modes, changing to some delays, changing clock phasing, and there's all sorts of stuff that you can twiddle. But it is pretty flexible, even in a fairly straightforward, simple implementation. There are a few other things you can do in software to optimise performance and overall throughput. Again, just taking the general case of grabbing an image and then just chucking it out of a serial port, where you could be throwing it to a display or maybe a radio link. The first thing is, what you don't need to do is, you start grabbing a frame, you've got your VSync, you sampled it. You don't need to wait until you've got a whole frame before you start sending it. All you need to know is that you've got at least one line. So if you look at what's happening here, it's sending, this is just a header byte, and it's using the DMA complete interrupt to say, the DMA on that line is complete, and we've got a foreground task that's just monitoring which line it's currently on and making a decision as to when it can send it. So what's happening here is that I've deliberately slowed the baud rate down a little bit here, so as soon as it's got the first line in, it can actually start sending it. Now the image parameters on this are such that it takes about twice as long to send it as it does to capture it. But there can be various other scenarios. So for example, at certain other zoom levels, like that for example, the actual send time is pretty much the same as the acquisition time. So in some cases, you don't even need a frame buffer at all in memory. If you implemented this instead of as a frame buffer, as a FIFO, you could, for example, capture, depending on the exact permutation of both the zoom level and the output resolution, you could actually end up being able to output quite a lot more of a frame than you actually have memory to store, because you don't need to actually store the entire frame in memory all at once. And again, I mean, if you're not changing any of the parameters, you don't need to worry too much about VSync. So for example, here we're capturing quite near the end of the frame. We're starting to send, but it's actually taking us into the next frame time to finish sending it. But that doesn't matter, because we don't really care what happens until the start of our next transfer here. So we don't actually have to wait for wait for a VSync. We just need to wait for the start of the transfer. The exception being, if we change some of the parameters, then we do need to wait for VSync, because that's the point we need to latch our our line positions, and we might need to, for example, update some of the camera I2C registers. But mostly things like our all our timer delays and so on, we would tend to latch those on VSync, because in particular the vertical position, we need to know that to know how many lines to count before we start. But for continuously acquiring with the same parameters, all we need to do is make sure that we've sent it by the time the next one comes along, to avoid needing to drop any frames, so we can maintain the maximum frame throughput. Now, of course, I've done this on a PIC because it's what I'm familiar with, but quite a lot of micros these days have DMA, so I'm sure it'd be possible to do this on quite a number of other micros, ARMs, various ARM processors or whatever. You can do it with interrupts. The problem is that the interrupt latency is sufficiently slow that probably going to end up having to slow the pixel clock down a lot, and also probably slow the frame rate down a lot. But obviously if you don't care about frame rate, that might not be an issue. But so as soon as you have DMA, you've got that method of getting data in quickly, and if you also have the ability to divide that pixel clock down, then that means you don't have to, you can immediately slow the data down significantly, particularly if you don't need colour. So if you do, then at the very least you need to be able to grab pixel pairs, and there might be ways of doing that. I mean, for example, there might be ways, for example, you perhaps add an external latch and run it into a 16-bit port. There's probably, again, there might be some processors that have facilities to do sort of 2 quick DMA cycles and then a gap, depending on the memory architecture. So it might be worth having a look at that on whatever your favourite processor is. But the nice thing about this PIC, it's got all the facilities. It's in a fairly sensible package. It's got an on-chip oscillator, so literally you don't really need any significant amount of external components. So there's a few of these camera modules around. Also, these breakout boards are quite readily available on eBay and AliExpress. These have got the 2.8 and a 1.8 volt regulator on them. This pin header is actually a fairly standard pin out. I think it originally came from some Omnivision evaluation modules, and you can find the pin outs in those data sheets. The only one that I have found are different are these ones, which have got Sunny on them. These are 9655 modules, and the pin out on this is completely different. And if you do find a module that's got a different pin out, I mean, these are so cheap, you know, you can just buy one. If you do actually come across one that's got a weird pin out that you're not sure of, yeah, these are generally so cheap that you can sort of usually sacrifice one just to trace the pins out. You can sort of just crack the lens holder off, and then either just cut or desolder the chip, which will be it's a BGA on there, and just literally check out each pin with a meter. The BGA pin out's generally in the data sheet. So the nice thing about these is they do come with a lens, but obviously you're pretty much stuck with that lens. So if you want a different lens, one option is you can just either screw the original lens all the way out. You can these they tend to be glued in, but you can usually crack the glue, and then they're quite easy to adjust. And either leave it like that or just take the lens holder off completely and then use an external lens like a standard M12 lens, and obviously there's all sorts of different viewing angles. You can get various things, including there's a few zoom lenses as well you can get in this format. So, you know, it's nice to have it with a lens, but it's not that difficult to use it with a different lens if you really need to.